Welcome you all to the course Database Management System. Myself, Muhammad Asifuddin Mundal, Assistant Professor, Department of Computer Science and Engineering, Narla Institute of Technology. And this is lecture number 36 for this particular course. I am going to cover chapter number 8, which is concurrency control. These are the topics which I am going to cover during my lecture. Here I am going to discuss about the concept of deadlock, when deadlock will happen in transaction, then if deadlock is there, then how to handle deadlock, then deadlock prevention technique. We will discuss also deadlock detection technique, as well as I will discuss about the recovery technique from deadlock. So before uh, stating what is the definition of deadlock, before that let's take a scenario when and how deadlock may happen in the system. Consider that partial schedule. From that schedule, we can understand that the system CPU executing two transactions at a time concurrently, T3 and T4, and T3 T4 accessing two data items A and B. Now CPU starts from T3, so CPU first will execute the transaction T3. So log XB means there is a data item B. Lock XB means transaction T3 make a lock request on B in exclusive mode lock. So what happened? Concurrency control component. There is a component concurrency control component. We check whether B is locked by any other transaction in non-conflicting mode or not. Now B is not locked by any other transaction, so concurrency control component will grant the request of T3. So B is locked in exclusive mode lock. I am denoting it in X. Exclusive mode lock, and it is logged by transaction T3. So transaction T3 will do the job. It will read the B, means it will transfer the content of B from hard disk to RAM. Then it will deduct $50. Then again write. It will write B means it will write back the content of RAM to hard disk. Then after executing this four instruction, CPU release the T3 and perform the context switch, and CPU move to the next transaction T4. Now T4 make a lock request on data item A. So this is set data item A. Make a lock request, and the type of lock request is S, means shared mode lock. Again, concurrency control component will check whether A has been locked by any other transaction in non-conflicting mode or not. So here A is not locked by any other transaction, so concurrency control component grant the lock request by T4. So A is logged in shared mode. I am denoting it as S. So it is logged in shared mode by T4. That's also fine, no problem with that. Now then T4 read the content of A, means it transfer copy the content of A from the hard disk to the local buffer of the RAM. That is also not a problem. It is also fine. Next, concentrate on that line. Again T4 make a lock request, and at that time lock request is being made on the data item B, and requesting mode is shared mode. So what happens? Same thing will going to happen. The concurrency control component will check whether the data item B has been logged by any other transaction in non-conflicting mode or not. So while checking that, concurrency control component will find that B is already logged by T3 in exclusive mode log, and T4 is also requesting to log the data item B in shared mode. So as we already know from the compatibility matrix, already we have seen in the last lecture that shared mode log, exclusive mode log are conflicting with each other. So what happens? Concurrency control component will not grant the lock request to log the data item B. So B cannot be logged by transaction T4. So what happens? CPU will not able to execute that statement. That means CPU becomes idle. So what happens? CPU will release, as CPU is not able to execute that particular line, CPU becomes idle. That is why CPU release transaction T4. And what happens? CPU will go back to the previous transaction, which is T3. Now in the transaction T3, what happened? Again concentrate on that line. T3 try to lock the data item A in exclusive mode lock. So again here what happened? Concurrency control component will check whether the data item A is already logged by any other transaction in non-conflicting mode or not. So in that case, concurrency control component will find that A is already been logged by transaction T4 in shared mode, and T3 is also making a lock request on A in exclusive mode. And as we know, shared mode and exclusive mode block is incompatible, as well as means exclusive mode block, shared mode block are incompatible. Shared mode, exclusive mode block are also incompatible. So that due to the incompatibility mode of locking, concurrency control component will not grant the lock request to transaction T3. So a data item cannot be logged by transaction T3. So that instruction and rest of the other instruction of T3 cannot be proceed, cannot be executed. So in that situation, what happens? Neither T4 can proceed his normal execution, nor T3 can proceed his normal execution. That means none of the transaction can proceed their normal execution from here on. So such kind of situation is called deadlock. So deadlock means a situation in the system due to which no one process or no transaction can proceed their normal execution. System becomes hanged. So this is called deadlock. So to handle the simplest way, how to handle the most simple technique to handle deadlock is either roll back T3 or T4, or you may roll back both. What about it? So simple way is to roll back any one of the transaction. If you roll back, then lock will be released. If lock will be released, then other transaction can proceed their normal execution. Now let's move to the next slide and state the definition of deadlock. So a system is in deadlock if there is a set of transactions such that every transaction in the set is waiting for another transaction in the set. That means uh, the system will be in their deadlock state if the system executing multiple transactions and each of the transaction in the transaction set are waiting for another transaction in the set. More precisely, or specifically if you speak, then we can represent it in other way also. Let me draw it. Suppose T is the set of transaction and suppose set consists of T0, T1 dot 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 set Tn minus 1 and Tn. Suppose these are the transaction set which are executing currently in any computer system T0, T1, T2 dot dot Tn. So in number of transactions are executing. Suppose T0 is waiting for a data item which is already held by transaction T1. But I am saying T0 is waiting for a particular data item which data item is already held by T1. That means we can represent it that way. So arrow towards T1 means T0 is waiting for T1. Why he is waiting? Because T1 is already holding a data item and that data item is already holding a data item and that data item is requested by transaction T0. Similarly, T1 is waiting for a data item. So T1 is waiting for a data item which is already held by T2. Similarly, it will continue to go like that. To continue to go like that. Next, what happens? For example, Tn minus 1 is the transaction Tn minus 1 is waiting for a data item which is already held by transaction Tn, and then Tn is the last transaction in the transaction set. So Tn will be waiting for the data item which is already held by the first transaction, means T0. So if you look at the diagram, this diagram, you can see that there is a circular wait or circular dependency between the transaction and the transaction. And I am repeating, transaction T0 says the first transaction, Tn is the last transaction. So T0 here waiting for transaction T1, T1 is waiting for transaction T2, T2 is waiting for T3, like that. Tn minus 1 waiting for Tn, and Tn is waiting for T0. Why they are waiting? Because suppose a particular data item is already held by T1. And at the same time, that data item is requested by T0, so T0 lock request cannot be granted, so T0 have to wait. Similarly, T2 is already holding a data item, and that data item is requested by T1, but lock cannot be granted because same data item cannot be accessed by two transactions, same thing. So T1 have to wait for the data item so that T2 can release. So that means there is a circular dependency out there. So this circular dependency will form a deadlock situation. Now, how to handle this? Two ways are there to handle a deadlock. First way is deadlock prevention, and second is deadlock detection and recovery technique. We'll see all these things in the next slide. Now the topic is deadlock prevention strategies. So deadlock prevention means a set of protocols which ensures that system will never enter into a deadlock state. That means deadlock prevention technique is basically nothing but a protocol, the algorithm which ensures that system will never enter into a deadlock state. Means deadlock will never happen if that algorithm execute in your system. Some of the prevention techniques are, it requires that one of the technique how to prevent deadlock, one of the algorithm is require that each transaction lock all of its data item before it begins execution. Means it's the concept of pre-declaration. Means before transaction starts its execution, before execution starts, the transaction needs to mention and needs to log all of the data item that is going to be needed during its execution time and execution cycle. But it has following disadvantages. That the first disadvantage is that it is not always possible to predict what are the data item is going to be needed. So it's very difficult to predict which data items are required. And second disadvantage is the data item utilization is very low. Why? Because before transaction begin execution, all the data item must be logged. But during execution time, at a single point of time, not all the data items are required by a transaction, only few of them are required. But even though few of them are required, but still you need to log all the data items. So data item utilization is become very low because no other transaction can access the data item. Once a transaction has been logged, once a particular transaction has logged the data items, so no other transaction can use them. So data item utilization is become very low. So these were the disadvantages if the transaction log all the data item before it begin their execution. And next prevention algorithm or the prevention technique is that we can impose a total ordering or partial ordering of all the data item that transaction is going to access, and require that each transaction can log the data item only in the specified order. So that means multiple data items are there, and we have to impose a ordering, means we have to impose an order on which the data item may be accessed. So transaction, while making a lock request, transaction can access the data item only maintaining those partial ordering. Already we have seen that in the graph based protocol or tree based protocol. In the next slide we will show many more developed prevention technique. Let's see. So this is the another scheme, weight tie scheme and wound weight scheme. But as the previous two techniques that I have discussed, there is no concept of timestamp were involved. But for these two techniques, the concept of timestamp is required. Means whenever the transaction enter into the system, each transaction assign unique and fixed timestamp. For implementing this two scheme, we needed timestamp based concept. So we'll discuss the first scheme, wait tie scheme. It's a non-preemptive technique, non-preemptive type technique. So let's discuss. Older transaction may wait for younger one to release the data item. Younger transaction never wait for older ones. They are rolled back instead. For example, suppose two transactions are there, Ti and Dj. Two transactions are executing currently in the system, and suppose Ti is and Ti is requesting a data item which is already held by Tj. Again I am repeating, suppose two transactions are currently executing in the system, Ti and Tj. And suppose Ti is requesting a data item which is already held by transaction Tj. Now in the wait die scheme, Ti is allowed to wait. Ti is allowed to wait only if the timestamp of Ti is smaller than that of Tj. That means smaller timestamp of Ti means Ti is the older transaction. So very simple way we can say that, suppose Ti is requesting a data item which is already held by Tj. So in that case, wait tie scheme, the system will allow the transaction Ti to wait for a bit if transaction Ti is older than transaction Tj. But if transaction Ti is not older than Tj, means Ti is younger, then what happen? Ti system will die the transaction Ti, means system will roll back the transaction Ti. So that means rollback means we can say that Ti is going to be die. Again I am repeating wait die scheme. So if a transaction waiting for a data item which is already held by some other transaction, then transaction which is requesting the item have to wait if the requesting transaction is older one, and if the requesting transaction is the newer one, then system will roll back, means it will die. That is why the name came from wait die scheme. That means from the perspective of requesting transaction, here the requesting transaction is the transaction which is requesting for the data item which is already held by other transaction. Here Ti is the requesting transaction. So either Ti have to wait or Ti will die. So when Ti will wait, if the transaction Ti is the older transaction, that means the timestamp of transaction Ti is smaller than that of Tj. And when Ti will die, if transaction Ti is new transaction, means if the timestamp of transaction Ti is greater than transaction Tj. That is why it is called wait tie scheme. And why it is called non-preemptive type means, in that case the transaction Tj is already holding the data item. So due to requesting by the transaction Ti, the currently executing transaction Tj is not going to be preempted by CPU. Currently executing transaction is Tj. Due to request by transaction Ti, CPU will not preempt, CPU will not release the Tj. CPU will continue with the Tj. That is why it is called non-preemptive technique. And the counterpart of wait die scheme is wound wait scheme, which is preemptive type. Preemptive type means, let's consider here TI and TJ. Two transactions are executing in the system. Uh, Same thing happened. TI is waiting or requesting a data item which is already held by TJ. Means TJ is currently executing and TJ already hold a data item, and same data item is requested by transaction TI. So here requesting transaction is transaction TI. Now in wound wait scheme, what happened? The older transaction wounds means force rollback of younger transaction instead of waiting it. Younger transaction may wait for older one. What does it means? Means if transaction Ti is older, means the timestamp of Ti is smaller than of Tj. That means Ti becomes older. So if transaction Ti is older transaction, that transaction Tj, then what happens? System will roll back transaction Tj. That means as if we can say that Tj is wounded by transaction Ti. Again I am repeating. Suppose Tj is holding a lock on a particular data item and same data item is requested by Ti. Now in wound wait scheme what will happen? System will roll back the Tj. Why? Because Tj is the newer one. So Tj is rolled back. So that means we can say that as if Ti has wounded the transaction Tj. So system will roll back the Tj as because Tj is a younger transaction. So Tj will be rolled back and it is termed as wounded by Ti. And if Tj is older one than Ti, means Ti is the newer one or the younger one than the Tj, then what happens? Then the requesting transaction Ti have to wait. In that case, Tj will continue, Ti have to wait. Ti have to wait. But if Ti is older one, then Tj will be rolled back, Tj will be wounded, then CPU will release Tj and CPU will, that means CPU release the Tj means CPU will preempt the Tj and then CPU will execute the Ti. That is why it is called preemptive scheme. So these are the scheme by which we can prevent the deadlock. And another very important point here is that though the wait die and wound wait scheme, the rollback is required, transaction rollback are required, but no starvation is going to happen because though the transaction are rolled back, but whenever transaction after rollback, whenever the transaction is restarted, they retain their original timestamp. Means when transaction enter into the system, they are assigned a unique fixed timestamp. Though they are rolled back, but while they are restarting, they will start with their original timestamp. So what happens? The older transaction does have precedence over new one, and so starvation is avoided. And another is the timeout based scheme where transaction request a lock and wait for a lock only for a specified amount of time, and after that the wait times out and transaction is rolled back. Means transaction requesting a lock for a particular data item and it is waiting for a long amount of time, and once the specified amount of waiting time has been over, then transaction is automatically rolled back by the system, and thus deadlock are not possible. And it is very simple to implement, and, but starvation is possible in that case. So though this is not a good technique. So wait time wound wait is the much more sophisticated one than timeout based scheme. Next technique is deadlock detection and deadlock recovery. Means if system does not employ the deadlock prevention technique, means that deadlock prevention technique is not there. So what happens? System will definitely enter into a deadlock situation. Means deadlock may be happening in the system if deadlock prevention technique is not employed there. So in that case, if deadlock is there, then what happens? We have to devise a technique by which we can detect the deadlock. Means we have to devise a technique which will detect whether deadlock is present or not in the system. And after that, after detecting, if it has been seen that deadlock is there, we have to recover from the deadlock. So we have to devise another technique for deadlock recovery. So first, let's discuss with deadlock detection technique. So deadlock detection, how to detect a deadlock? For detect a deadlock, we need a graph which is called wait for graph. So this is wait for graph. It's very important. And as usual, the wait for graph is a graph. The purpose is to represent the deadlock scenario. With the help of wait for graph, we can represent the deadlock state in a system. And wait for graph, like any other graph, is represented in the form of G is equal to V comma E, where V is a set of vertices and E is a set of edges. Now here V is a set of vertices, it represents all the transactions are currently executing in the system, where E is a set of edges and it is represented in the form of Ti to Tj. The question is, when we can write Ti to Tj? If Ti arrow Tj is in edge set E, that means then there is a direct edge from Ti to Tj. This implies that Ti transaction is waiting for transaction Tj to release a data item. That means Tj is already holding a data item and Ti is make a request to that same data item. So Ti have to wait for transaction Tj to release the data item. So if that is the case, then we can insert a arrow from Ti to Tj. And when transaction Ti requests a data item currently being held by Tj, then edge Ti arrow Tj is inserted in the wait for graph. That means if Tj is currently holding a lock and same data currently holding a lock on data item and same data item is requested by transaction Ti, then we have to insert that arrow in the wait for graph. And this edge is removed only when Tj is no longer holding the data item. So when Tj release the data item, so Ti doesn't have to wait. So we remove that arrow from the wait for graph. Next, the system is in deadlock, so that means with the help of this concept, we have to draw the wait for graph. Now, after drawing the wait for graph, we can detect easily the system is in deadlock state if and only if the wait for graph has a cycle. Means if the wait for graph has a cycle in it, then we can straightway say that the system is in deadlock. And all the transactions involving in that cycle are said to be deadlock. And if the wait for graph has no cycle, then system is not in deadlock state. Let's take an example of wait for graph. This is the wait for graph and this is also wait for graph. First consider this one. So here vertices, these are the vertices, circular vertices, and they correspond to the individual transactions. Now the transaction T25, arrow transaction T26, that means the arrow plus T26 means we can say that T25 is waiting for transaction T26, means T26 is already holding a data item and that data item is requested by T25. That means transaction T25 is waiting for the data item which is currently holds by T26. So T25 have to wait for T26. As well as T25 is requesting a data item which is currently holds by T27 also. So T25 has to wait for T27 also. Also, T27 is waiting for a data item which is already holds by T26. Similarly, T26 is waiting for a data item which is already holds by T28. So this is the scenario. So the edges are also being inserted. If you look at this wait for graph has no cycle in it. That is why we can say that the system is not in deadlock state. they can proceed their normal execution. But if you consider this one, age towards 26 from 25 means T25 is waiting for T26, T25 is waiting for T27, now T27 is waiting for T26, T26 is waiting for T28, and T28 is waiting for T27. If you look at this portion only, you can easily identify that this is a cycle starting from, say, starting from T26, writing here transaction T26 waiting for T28, next T28 is waiting for T27, and T27 is waiting for T26. This is what the definition of deadlock I've already mentioned in the beginning of this lecture. Means there is a circular wait among the transactions. So it will be not here, it will be over here. So T26 is waiting for T28, T28 is waiting for T27, and in turn T27 is waiting for T26. That means there is a circular wait among the transactions. So cycle is there in the wait program. That is why the system is in deadlock state. So in that case, transaction cannot proceed its normal execution. So with the help of deadlock detect, with the help of wait program, we can detect. So for detection, we need to devise an algorithm. The algorithm will read the wait program and check whether cycle is there or not. The next is deadlock recovery. Once the deadlock has been identified, deadlock detection has been identified, detection is identified, deadlock has been identified, then we have to recover from deadlock. So first what we have to do, first we have to select a victim, means which particular transaction or the set of transaction that needs to be rolled back. So first step is to select a victim or made a victim. So this is the first step. Once the deadlock has been detected, we have to select the transaction or transactions. Those are needs to be rolled back and they are known as victims. So we have to select the victim. Now, how to select a victim? It will be based on minimum cost. Now, what does it mean? Minimum cost, specifically speaking, the transaction minimum cost, it means it will select only those transactions based on how long it has already been executed, how much more time it will take to complete the execution. This is the first technique. If transaction executed long enough time and it remains a little bit amount of time to complete the execution, then it will incur maximum, it will incur or produce maximum cost. The cost associated will be high. Second the second criteria of cost is how many data items it has been already acquired and how many more data items it will require. If a transaction requires small amount of data to complete this execution, then it will incur minimum cost. But if the transaction requires huge number of data items, still, then it will incur maximum cost. So based on this criteria, we can select a victim. So the transaction which will incur the minimum cost are selected as a victim. Next, we have to go to next. Once the victim are selected, we have to roll back. Roll back means we have to undo the effect, whatever it has been done. On rollback can be of two types. Total rollback. Total rollback means the selected transaction or the victim transaction needs to be aborted and restart it. This is for total rollback. Another is partial rollback. means we are not going to roll back full. Means we cannot restart it from at the beginning. Rather, we will have to roll back up to the point from where if we roll back, then data item will be released and other transaction can proceed the normal execution. That is called partial rollback. And also, third important thing which we have to remember in deadlock recovery is starvation. Starvation happens if same transaction is always chosen as a victim. So, how to overcome that? There is a threshold should be there that a particular transaction will be selected as a victim for a specified amount of time. If the specified amount of time is already over, then we cannot select that particular transaction again. So that criteria can be included in the criteria to select a victim. So that's all for today. This is all about deadlock detection, deadlock prevention, and deadlock recovery techniques. And these are the references you may go through for further.